Hi everybody, I hope this video finds you well. In today's video, we're going to be wrapping up section 7.7 from your textbook, which was our discussion of numerical or approximate integration. So far, in the previous two videos, we went over some of the basic approximation methods, such as left endpoint and right endpoint. We introduced some slightly more interesting and slightly better approximations, the midpoint approximation and the trapezoidal rule approximation. And then in the previous video, we investigated error-bound formulas for those two better sort of approximations, the midpoint and trapezoidal rule approximations. In this video, we're going to wrap up section 7.7 by talking about a slightly more advanced method called Simpson's rule. And for this, we're going to not only talk about the summary of Simpson's rule, how do you actually use this rule, but also its error-bound formula. As we'll see, Simpson's rule is a lot more accurate than the sort of midpoint and trapezoidal rules, but it does come at sort of a cost that it is a little bit of a more complicated expression to actually use Simpson's rule, and the derivation of Simpson's rule is definitely a lot messier because of the sort of geometry involved. So, Simpson's rule is a more advanced and, again, more accurate method for estimating a definite integral. So the way you actually construct Simpson's rule, the way you sort of derive it, is you use shapes that have a rectangular base but with a parabolic top. And what we're basically sort of trying to do there is we're trying to sort of extend the idea of the trapezoidal rule. If you think about what the trapezoidal rule was doing, it was sort of saying, let's let a sort of rectangular base, but then use a sort of diagonal line or a straight line as the sort of top. And we estimated that line by taking 2 points on the curve and sort of drawing the line between them. What Simpson's rule does is it extends that idea and says that instead of trying to make that a straight line, well, oftentimes you're trying to estimate like a curve, so why don't we actually use a top that is a curve shape? Now, there's many curve shapes out there, but one of the easiest ones for us to work with is a parabola. So if you take 3 points, if you have your sort of curve, and you take 3 points on that curve, then you can determine a sort of parabolic shape, a parabola, that tries to estimate those the sort of parabola that goes through those 3 points. Now, the derivation of this, because you have to fit a parabola through 3 points, which in and of itself is a sort of messy algebra problem, and then to actually get the area under that parabola, you actually need to integrate that parabolic shape and actually use an integral formula, not just a geometric formula. The derivation of Simpson's rule is pretty messy. So you can read through the derivation in your textbook if you're interested, but instead for our class, I'm going to focus more on how you use this approximation and also the error-bound formula for this approximation. So we're not going to go through exactly the sort of diagram and derivation of Simpson's rule. Instead, we're just going to jump straight to the summary. So, for the summary of Simpson's rule, we're going to suppose, again, we have f of x a continuous interval on a to b, and again, we're going to choose n to be the number of partitions. One small detail is that the way that you sort of do these parabolic tops is you sort of do them by taking 3 points and then using the last of those 3 points as the start of the next. So, what that means is that the n must be an even number of partitions. So, Simpson's rule is only done when you want an even number of partitions. You cannot perform Simpson's rule with an odd number of partitions. The size of each partition, delta x, is still calculated as b minus a over n, and we still consider x0 to be the start of our interval, x1 to be x0 plus delta x, all the way down to the very last one, x sub n, which is the same as the end of the interval, b. Then the Simpson's rule approximation, s sub n, is equal to delta x over 3. So outside, similar to the trapezoidal rule, we have delta x over 3. And then inside, we have this sort of pattern of that we start with f of x0, then plus 4 of f of x1 plus 2 of f of x2. This pattern will go 4, 2, 4, 2, so on and so forth, until we get down here to 2 of f of xn minus 2, plus 4 of f of x minus 1, and then plus f of xn. So you'll notice that the first and last have 1s, and then the pattern in the middle is 4, 2, 4, 2, 4, 2, etc., until you end on 2, 4. So it'll always begin with a multiple of 4 and end with a multiple of 4, and the very ends are always just single factors, no multiplication there. So this is our Simpson's rule approximation. In a few moments, we'll do an example of actually setting up this approximation for a definite interval. Also interesting, though, is the error-bound formula for Simpson's rule. We introduced error-bound formulas in the previous video for the midpoint rule and the trapezoidal rule. Remember, these give us a bound for the maximum error. They don't tell us what the exact error was going to be, but they tell us the worst-case scenario for the error. So the error-bound rule for Simpson's rule is that we have a function f of x on an interval a to b. Then we're going to suppose that capital K is an upper bound on the fourth derivative, the absolute value of the fourth derivative. So I just want to make a note here. This is the fourth derivative. So we're going to have to calculate the fourth derivative here. So, and then K is the maximum value of the absolute value of that fourth derivative on the interval a to b. Then you have this error bound for the error in terms of Simpson's rule. The absolute value of the error is less than or equal to that capital K times b minus 8 to the fifth over 180 n to the fourth. Now, you might look at this and say, how does this sort of tell us that Simpson's rule is more accurate? Well, you'll notice that the partitions down here go to the fourth power, so the accuracy goes way up much more quickly based on a higher number of partitions than it does for like the midpoint or the trapezoidal rule where there's only an n squared down there. So this gets very small very quickly based on larger and larger values of n. So that's why Simpson's rule, you can get very accurate results with a smaller number of partitions than you can with midpoint or trapezoidal rule. So the two main things to take away from this is the actual formula for calculating a Simpson's rule approximation and the error bound for working with Simpson's rule. So let's jump into a couple examples. During these examples, though, we'll also review some of the earlier stuff we talked about with the midpoint and trapezoidal rule. So for this first one, what we're going to do is we're going to consider this definite integral, the integral from 2 to 4 of ln of 1 plus x squared dx, and we're going to simply just write down but not evaluate expressions for m6, t6, and s6. So the midpoint rule, trapezoidal rule, and Simpson's rule with 6 partitions. So to start off with here, let's get our delta x. So that's going to be our b minus a, 4 minus 2, divided by the number of partitions, which is going to be 6. So 2 over 6, which is 1/3. So the spacing of our partitions is going to be 1/3. Let's go ahead and give ourselves a number line to sort of work with. We'll start our number line at 2 and end it at 4, and we'll go by 1/3. So I guess that this would be 7/3, and then 8/3, and then 3, and then 10/3, and 11/3, and then we would end at 4. So let's go ahead and do our midpoint rule. So we'll do these in different colors just for fun. So for the midpoint rule, of course, unfortunately doesn't use any of these. It uses the midpoint between each of these. A little bit messy to do that, but if you think about this as 6 over 3 plus 7 over 3 divided by 2, I guess that's 13 over 3 divided by 2, which is 13 over 6. So our first midpoint here is going to be 13 over 6. Then, because I know my gap is 1/3, which is equivalent to 2/6, I can just add 2/6 to this to get the next midpoint, which is going to be 15 over 6, then 17 over 6, then 19 over 6, 21 over 6, and 23 over 6. So these 6 values are going to be the 6 approximations used for the midpoint rule. So the midpoint rule is going to be delta x, which is 1/3, times f at 13 over 6 plus f at 15 over 6 plus f at 17 over 6 plus f at 19 over 6 plus f at 21 over 6 plus f at 23 over 6. And last thing we need to say to set this up is what do we mean by f, or what function are we using there? Well, of course, f of x is the function we're trying to perform the definite integral of, which is 1 plus x squared. Ln of 1 plus x squared. So this right here would be a totally appropriate way to write down what we mean by write down but do not evaluate an expression for m6. So there we go. All we would need to do if we wanted to evaluate it is plug each of these values into this, add them all up, and then multiply by that 1/3. All right, let's go ahead and do the trapezoidal rule. So now we'll go ahead and do T6. Remember, T6, you will go ahead and use each of the original values, not using those midpoints, but we're going to actually use each of those ends of each interval from the partitions. Then outside of this, we're going to have our delta x over 2. Then remember, for the trapezoidal rule, the first one, f of 2, has no coefficient. Then we're going to have 2f of 7/3 plus 2f of 8/3 plus 2f of 3 plus 2f of 10/3 plus 2f of 11/3, and then we're at our very last one, and remember this would only be used as the right end, the right height of the last trapezoid, so there's no extra factor there, so we just have f of 4, close up our parentheses, and again make the note that f of x, of course, is just ln 1 plus x squared. So again, since we're just trying to set it up but not evaluate it, there we go. All right, last one. Let's go ahead and do our Simpson's rule. So Simpson's rule, similar to trapezoidal rule, we're going to use the same points. So we're just going to use those actual ends of our partitions. It's not using the midpoints or anything. So there we go. So out front, we're going to have 1/3. That's our delta x divided by 3. Then we're going to start with f of 2. Then the first one gets a factor of 4. So 4 times f of 7/3. Then a 2 times f of 8/3. Then back to 4, f of 3. Then 2 f of 10/3, sorry. Then 4 again, f of 11/3, and then we're on our last one. So just like trapezoidal rule, it doesn't get any coefficient, f of 4. So there we go. Notice that this pattern goes 4, 2, 4, 2, 4. It always starts with a 4 and ends with a 4, and then of course the very first and the very last have no coefficient at all. So there would be the Simpson's rule approximation, and again we should just make a note, f of x here of course, still just going to be ln 1 plus x squared. Okay, so there we go. There's our 3 main approximations. These are really the ones that we want to be comfortable with in our class. Left endpoint and right endpoint, of course, are also important, but you covered those a lot in your Calc 1 classes. These are really the ones that we're covering in this class, so make sure you're comfortable writing down the expressions for each of these approximations. This is also usually the form that you'll be asked about in our class for like a quiz or an exam. We're not really interested in having to plug all these things. That's just a lot of calculator arithmetic type stuff. So this is more the format that we'd like to see our sort of answers in, especially when it says write down but do not evaluate. Okay, now let's turn our attention to looking at some of that error-bound stuff. So now we're going to look at a new example. Now we're going to consider this definite integral, the integral from 4 to 9 of x to the 5/2 dx. What we're going to do is we're going to try to figure out the number of partitions necessary to approximate this integral to within 0.05, so we only want to be off by 0.05, using the trapezoidal rule, midpoint rule, and then Simpson's rule. So let's go ahead and start with A. Oh, we'll need to go ahead and do that. So for A, we're going to use our error-bound formula for the trapezoidal rule, which is supposed to be that that is less than k b minus a cubed over 12n squared. So that's our trapezoidal rule formula. And of course, we want that to be less than 0.05 because we want to make sure that we're within 0.05. Okay, so let's go ahead and think about what we sort of know here. We're going to need to figure out our A, B, and K to plug into this. Of course, we know the A and B. The A is 4 and the B is 9 here, but we're going to need to determine this K. So when you're working with the trapezoidal rule or the midpoint rule, this K is based on the second derivative. So let's go ahead and do that. So remember little k here. K is an upper bound on the absolute value of the second derivative on the interval 4 to 9. So we have f of x, which is x to the 5/2. We have f prime, which would be 5/2 x to the 3/2. And then we have f double prime, which if we drop that 3/2 down, looks like it'd be 15 over 4 x to the 1/2. So there's our second derivative. Clearly that's always positive, so the absolute value of f double prime is also equal to 15 over 4 x to the 1/2. Now, the thing we want to focus on is that x to the 1/2. As you plug larger numbers into x to the 1/2, well, the square root gets larger, right? The square root of a small number is small, the square root of a larger number gets larger, right? Especially on an interval like 4 to 9. So what we want to go ahead and do then is we want to choose the largest thing. Since this is strictly increasing, so since absolute value f double prime is strictly increasing, we want to choose, since this is just going to get larger and larger, we want to choose the large end of our interval. Let's go ahead and choose x equals 9. So we'll go ahead and plug that in. We'll get k is going to be the absolute value, f double prime at 9, which is going to be 15 over 4 times 9 to the 1/2. 9 to the 1/2 is 3, so I guess we get 45 over 4. So if we go ahead and pop all that stuff in, then what we can say, taking this down here, remember this is what we want to focus on, this side here, we can go ahead and get 45 over 4. I guess just for consistency, I'll go ahead and bring this up here just to remind ourselves that's why we were doing this. So we get 45 over 4 times 9 minus 4 cubed over 12 times that n squared, and of course n is what we're looking for, and that's supposed to be less than 0.05. Now at this point, you want to just go ahead and solve this. I guess we could multiply the 12n squared over. So this would imply that we would get 45 over 4 times 5 cubed is supposed to be, and then 12 times 0.05 is it's going to be 0.6n squared. And then that would tell us that if we would get the square root of 45 over 4 times 5 cubed divided by 0.6 is supposed to be less than n. That's just dividing the 0.6 over and then square rooting. If we go ahead and type that into a calculator, so we have the square root of 45 divided by 4 times 125, because that's what 5 cubed is, then divided by 0.6. Let's see what we get there. That looks like we should get that this implies we're going to need 48.4 is less than n. Remember, n has to be an integer value, though, because it's the number of partitions. So we need at least 49 partitions to estimate to within 0.05 using the trapezoidal rule. All right. So this is just sort of a review of what we had done in the previous video, just wanting to make sure we're still comfortable using these error bounds that we established beforehand. Okay, let's rinse and repeat and do this for part B using the midpoint rule. So we'll go ahead and we'll do this for part B now. So for part B, we want to do this for the midpoint rule. So we're going to remember that the midpoint rule, error bound, is that this is supposed to be less than or equal to k b minus a cubed over 24n squared. So here, our a is still going to be 4, our b is still going to be 9, and our k is also not going to change because remember, for both the trapezoidal rule and the midpoint rule, the k is based on the second derivative. We already did that, so we know that k is still going to come out as that 45 over 4. So we can go ahead and let this be less than 0.05. That's what we want. We want this error, which we know is less than this, to be less than this. So we can go ahead and set this up. This is going to be 45 over 4 times 9 minus 4 cubed over 24n squared less than 0.05. Again, we can start by multiplying that 24n squared over to the other side. 24 times that 0.05, that's going to give us a 1.2. So it looks like we're going to get 45 over 4 times 5 cubed is less than 1.2 n squared. And of course, then that's going to give us 45 over 4 times 125 divided by 1.2 and square rooted needs to be less than n. And that is going to imply for us, if we feed that into our calculator, the square root of 45 over 4 times 125 divided by 1.2. And that looks like we should get 34.2 is less than n. And again, got to have an integer value that is larger than this. So we could say we need at least 35 partitions to estimate to within 0.05 using midpoint rule. So this is sort of interesting, right? We need at least 49 partitions for the trapezoidal rule, but we can get away with only 35 partitions when we're doing the midpoint rule, which means that we need less partitions to achieve the same sort of level of accuracy. Now let's try this for our new one, Simpson's rule. So we'll give ourselves one more sort of page here. Okay, so same thing. We're going to set up the error bound for Simpson's rule, which is supposed to be less than or equal to capital K, b minus a to the 5th, over 180 n to the 4th. Now here again, we're going to need to know a, b, and this capital K. And again, we want this to be less than 0.05. So a is still 4, b is 9. Unfortunately, we cannot say that k is 45 over 4 anymore, because now this is supposed to be based on the 4th derivative. So over here, we're going to have to remember that k is an upper bound on the absolute value of the 4th derivative. Well, we can sort of go back and remember, I mean, we don't have to start from scratch. We actually figured out the second derivative. We already had the second derivative here, so we can just start from there. So we can just say, recall that f double prime was 15 over 4 x to the 1/2. And we can differentiate again and get f triple prime. Looks like it should be 15 over 8 x to the negative 1/2. And then we can get the fourth derivative. If you ever want to just be careful, if you're worried about confusing the derivative with the power, you can put parentheses up there, and that signifies derivative. So then when we do this, you can get a negative 15 over 16 x to the negative 3/2. Now this is sort of interesting. This time it's actually negative, so applying the absolute value is going to matter. So the absolute value of the fourth derivative is actually equal to 15 over 16 x to the negative 3/2. And if you're a little hesitant about that negative 3/2, remember we can just think about that as 15 over 16 x to the 3/2. Now what's interesting about this is that this is a strictly decreasing function, unlike the second derivative, which was strictly increasing. Here, the larger x is, the smaller this gets. So this time, this fourth derivative here is strictly decreasing. So what we want to do to make sure that this is as large as possible is choose the small end of our interval. So we're going to choose x equals 4. That means k is going to, capital K is going to be the absolute value of the fourth derivative evaluated at 4, which is going to be 15 over 16 times 4 to the 3/2. And of course, 4 to the 3/2, I mean, we could just leave it there, but that's going to be, the square root of 4 is 2, so that's going to be 8. So I guess we would get 15 over 8 times 16, which is going to be 128. So there is our capital K this time. Now, this is something really important here. I want to just make sure you guys compare and contrast this between the little k. Remember, little k here was based on the second derivative. The second derivative turned out to be a strictly increasing function. The larger x was, the larger this was. So we chose x equals 9 to make it as large as possible. For this one, though, by the time we had gotten to the fourth derivative, the x was now in the denominator, meaning that it was strictly decreasing. So we wanted to choose the smaller x value to make sure that this was still as large as possible. If you chose x equals 9, this would actually be smaller than what we originally got here. And remember, we want k to be an upper bound. So we chose x equals 4, and that gave us our capital K here. So now we are ready to put this all together. So we have 15 over 128. Times 9 minus 4 to the 5th over 180 n to the 4th, and that's still supposed to be less than 0.05. So we can begin by going ahead and multiplying this over onto the other side. If we do that, looks like we should go ahead and get 15 over 128. 5 to the 5th is supposed to be less than 9 n to the 4th. Then we can divide that 9 over and take the fourth root. So it looks like we get 15 over 128, 5 to the 5th, over 9. And then we're going to take the fourth root of that. And that is supposed to be less than n. So now it's time to just feed that into a calculator. So we'd have 15 over 128 times 5 to the 5th. And then divided by 9, and then all of that raised to the 1/4 exponent. So if we do all of that, it looks like what we should get there is we get that this implies that we have about 2.5 is less than n. So n needs to be an integer value that is larger than 2.5. We might be tempted to pick 3, but keep in mind that with Simpson's rule, n must be even. So we need at least 4 partitions to estimate to within 0.05 using Simpson's rule. So we can see that we can get away with a tremendously small amount of partitions. Only 4 partitions are necessary to estimate to within 0.05 using Simpson's rule. Then contrast that with needing, 49 partitions, so 49 approximations when we did the trapezoidal rule, and then slightly better, 35 to do the midpoint rule. We can get the same level of accuracy with only 4 partitions for this Simpson's rule. So this really does show you that despite the complexity of the Simpson's rule, it is pretty useful considering the high level of accuracy for the small number of partitions. This pretty much concludes section 7.7 for us. In our next video, we'll be moving into section 7.8, turning our attention away from approximate integration to what are called improper integrals, which are going to be integrals that either extend to infinity or involve discontinuities.